So the other day, we worked on our stations. We had 5 stations in the back, and we just kind of rotated through them. So for the first one, chemistry is the study of the composition of matter and the changes that matter undergoes. So this is our definition of chemistry. So chemistry is the study of matter. And then in your textbook, you were supposed to define the term matter and give 3 examples. So matter is anything that has mass and takes up space. Okay, so matter is anything that has mass and takes up space. So anything, trees, your textbooks, and even you're all examples of matter. Okay, when you think of the word mass, it's often confused with weight. Right? Mass is often confused with weight. When we think of mass, we think of anything that's heavy, anything that's massive. So weight is equal to mass times gravity. And since we're on planet Earth, everything that has mass has weight. Okay, so we often use them interchangeably, but mass is just this idea of the number of what we call protons and neutrons. Okay, so mass is anything that is made up of atoms, anything that has those protons and neutrons. Okay, so everything in our world is made up, or everything material is made up of atoms. So an advertisement for juice drinks that says juice is all natural or free of chemicals, if chemistry is the study of matter, and matter is anything that has space and takes up space and has mass, then juice itself, or the molecules that make up juice, those are chemicals. Right? And that's because chemicals is just a fancy word for molecules and atoms. Okay? So we move on to station number 2. Station number 2 was those 5 areas of chemistry. So for us, the areas of chemistry are often blurred. They are not exclusive, okay? So a biochemist can use analytical chemistry techniques. So the thing that I was mostly looking for you to match up is the study of. So we had our 5 areas of chemistry: organic, physical chemistry, inorganic chemistry, biochem, and analytical chem. Okay, so these are our 5 areas of study. So we're going to start with what they're actually used for. What are they, or we're going to start with what they study. So it's the study of something. So each one of these is the study of something. Organic chemistry, so if we take these away, organic chemistry, you might remember from biology, is the study of any chemical that contains carbon. So all carbon-based things are organic chemistry. And that's a simplification, but it's a simplification that'll get you through high school and most of college. Okay? So plastics are made of carbon. Okay, plastic, the base molecule in plastic is carbon. You could also have put, it's used to measure the level of carbon dioxide, right? That's carbon, it contains carbon. So either of those examples could be, or either of those uses could be done by organic chemistry. Okay? So either one of those is just fine. The next one, if we move to inorganic chemistry, so if organic chemistry is the study of all things containing carbon, then inorganic chemistry is the study of anything that doesn't contain carbon. Okay? So inorganic chemistry, anything that doesn't contain carbon, could be metal materials, so used to develop metal materials. Metals aren't carbon. So metals, obviously, iron, copper, zinc, right? Those are all your metals. You could also put, well, for this one, mostly metal. Everything else, most of the time, contains carbon. So for inorganic chemistry, don't contain carbon and used to develop metal materials. Okay? Our next area of study could be physical chemistry. So physical chemistry is the study of mechanisms, rates, and energy transfers. Okay? So physical chemistry, when you get to college, it's this area, this class you take all on its own. And you actually study reaction rates, you study thermodynamic transfer. So we're going to study thermodynamics later in the year. But the key here is mechanisms and rates. So remember from biology again, catalysts are used to speed up the rate of a chemical reaction. So physical chemistry would be used to study how a catalyst would affect the rate of reactions of photosynthesis in trees. Okay, so physical chemist, the key here is that it's the reaction rate. We're studying the reaction rate. Next is biochemistry. So biochemistry is the study of things that take place in living organisms. You get that hint from bio. So biochemistry is anything that takes place in a living organism. And biochemistry could be used for studying how the catalyst affects photosynthesis in trees, right? So trees are living organisms. Photosynthesis is something that happens in a living organism. So you could have said this one, absolutely. But more often than not, biochemistry is used to study how the energy that's produced for muscle contractions is made and stored. Okay, so muscle contractions in the body, we look to see how that energy is made and how it's stored in your body. And then finally, last but most certainly not least, analytical chemistry. This one's the trickier one. It's the study of quantitative composition of matter. So quantitative just means numbers, okay? Quantitative. Analytical chemistry gives us numbers. It tells us how much of something, or mostly how much of something. How much of something we have, how often it's produced. So analytical chemistry would be used to measure the level of carbon dioxide. So if you ever see, it's used to tell us amounts or levels or how much. That's your key that you're dealing with an analytical chemistry technique. And that's not to say that a physical chemist couldn't measure the levels of carbon dioxide, or a organic chemist couldn't measure the levels of carbon dioxide or pollutants. Okay, they're all interchangeable, but these are the basics. So analytical chemistry is a study of numbers. How much matter is there? Okay. If we move on to Station 3, Station 3 was our scientific method. So the scientific method is a systematic approach to a solution of a problem. Okay, I gave you a bunch of steps. So our steps, the purpose of this experiment was just to see if you could come up with a logical, step-by-step solution. Okay, so the key to the scientific method is you're defining a problem based on a specific body of knowledge, right? You're coming up with a question based on what you already know. Okay, that's what the scientific method does. So in biology, chemistry, physics, and earth space, you're always doing these, but maybe not in this exact order. So if you had, let's say, examined books and other sources to see what's already known after you had already, or before you posed your question, that's absolutely fine, right? If you had look at the resources and then come up with a question, that's absolutely fine. As long as you're doing these steps, that's the important part, right? And then obviously coming up with your answers is going to go after coming up with your questions. Coming up with your explanations is going to go after you've done your research. So as long as you have this general order, that's what I was looking for here. And as long as you have an explanation to back up your logic, okay? If we go on to station 3, or station 4, my apologies. Station 4 was the broken flashlight. So if you have a broken flashlight, you notice it doesn't turn on, you want to come up with a hypothesis. Why isn't the flashlight working? So it could be the batteries are dead or missing, right? Remember, a hypothesis is an explanation. Okay, so this, suppose you turn on a flashlight, it doesn't light. This is your observation, right? The flashlight doesn't light, that's your observation. Your hypothesis is an explanation for why it doesn't light. So it could be the batteries are dead or missing. It could be that the light bulb it could be that your switch is broken. Okay, all of these are viable or acceptable explanations for what you're seeing. They're all acceptable hypotheses, right? They have to be testable. So remember, a hypothesis, you have to be able to actually test it. So then you come up with explanations that you could, or experiments you could do to test. You can replace them, right? Replace the batteries. If the light bulb is dead, replace the bulb or replace the switch, right? You can just replace the problem, get a new one. You could test the batteries in another flashlight, right? If the batteries are there, but they might be dead, you can test the batteries in another flashlight to make sure that it's not the light bulb, right? Or to make sure that it's not the batteries, maybe it's the light bulb. So there are lots of different experiments you could come up with to test this hypothesis. And then lastly, I ask you to define the terms and give an example from your flashlight scenario. So your dependent variable is the thing that depends on, so your dependent variable does not change. Okay, your dependent variable does not change. It's the thing that you're observing. What are you observing? So in this case, we're observing the production of light, how much light is made. Okay, so our production of light is our dependent variable. Our independent variable is what you change during the experiment. Okay, it's what you changed during the experiment. So if we changed the switch, the batteries, or the actual light bulb, those would all be our independent variables. Okay, the answer for this is going to be based on what your experiment was, what your hypothesis was.